Hello, hello. We have part two of this chapter on electrochemistry. So, picking up, we should know how to calculate cell potential using standard reduction potentials that you could look up in a table, or we should be able to calculate it from different equilibrium constants and all sorts of stuff. So, to continue on, we're going to look at, well, how do we calculate it with non-standard state conditions? Remember, standard state is at 1 molar concentrations. So what if it's not? So we have this equation from the last chapter that Gibbs free energy at non-standard conditions is equal to um, the standard Gibbs free energy plus constant temperature and the natural log of Q, which was our equilibrium constant or quotient. Yeah, not constant, quotient. So at non-equilibrium. Well, we also know from the last chapter, actually no, in this chapter, that in terms of chemical energy, that NFE, negative NFE, is the amount of energy in the form of electrical work that can be done for delta G. So again, N is number of electrons, F is Faraday's constant, and we could also say the same thing for delta G standard or delta G naught. So at standard conditions, same thing. So the amount of energy, the overall charge, that's what NF is, times the cell potential. Well, if we substitute those two, we get this. And then if we factor out by dividing both sides by an F, we get a very famous equation called the Nernst equation. And the Nernst equation helps us figure out what is the electric cell potential, the cell voltage, the electromotive force when we are at non-standard state conditions. So more specifically, at usually talking about different concentrations in a galvanic cell or even battery. So it's the standard cell potential minus a constant times temperature divided by how many electrons divided by a mole of electrons times the natural log of our reaction quotient. Now, typically, we're going to say we're at 25 Celsius, 298 Kelvin, and R and F are both constants. So we can plug all that in and we get this. So this is usually the form that I would give you and the form that you'll see me using. This is for, the more general version up here for different temperatures and stuff, but 0.0257 volts divided by moles times natural log Q, subtract that from standard potential, and you have your answer. Now, if you like your old school base log, base 10 log, there you go. I won't be using that. But again, what this does is it allows us to calculate cell voltages when we're not at 1 molar conditions, because, well, we're not always going to be at 1 molar, or even if we were, as the reaction progresses, the molarity changes. So let's try that. Let's use the Nernst equation to find the cell voltage when we have a 0.15 molar solution of a cobalt ion, and iron ion is at 0.68 molar. So we want to know, would this reaction be spontaneous? So what we're trying to figure out is when we calculate E, what is its sign? Because if it has a positive cell potential, a positive E, it would be spontaneous. But if it's negative, then we know it's not spontaneous, but we're going to quantitate it. So again, this is a redox displacement reaction. Here we're looking at pretty much the net ionic equation where whatever spectator ion is not shown. So cobalt is getting oxidized, iron is getting reduced. So here's the Nernst equation where we're saying it's at 298 Kelvin and everything else plugged in. So there's a couple of things we need. We need to find Q, our equilibrium quotient, and I know some of you are probably suffering from PTSDs anytime I say the word equilibrium, but remember that quotient is going to be the products times um, their raised to their coefficients divided by the reactants raised to their coefficients. But we never include solids or pure liquids, so really the only thing we're going to include in the aqueous thing. So the cobalt ion over the iron ion concentration. And look, we have those right here. Yep, that's easy. So then we also need N. So this is just, if we look at the half reactions, again, cobalt's getting oxidized by losing 2 electrons. Iron is getting reduced. It's gaining 2 electrons. And so our N is 2. There's 2 electrons being transferred. And then we need our cell potential, our standard cell potential. So that E naught, we get this by going and looking up the tabulated data. So we can look up the standard reduction potentials for iron to go from 2 to 0, as well as cobalt to go from positive to neutral. And again, iron is serving as our cathode because it is getting reduced, and cobalt is getting oxidized, so it is our anode. So here's what that looks like. Here's the resolution of that's terrible. Here's that equation. Again, we're going to look up iron and it's negative 0.44. We're going to subtract cobalt, which is negative 0.28, and we get a standard reduction potential of negative 0.16. So if we were to just say right now, under standard conditions, would this reaction go? The answer would be no. Under those conditions, a negative voltage would not be a spontaneous reaction. But we're not at standard conditions. We have these concentrations. And so if we go ahead and plug in, there's the negative 0.16 volts divided by 2 times our concentrations, we end up with negative 0.14. And so it's slightly closer to 0, but since it's still negative, it is still non-spontaneous. Now, if we wanted to figure out exactly at what concentrations could this reaction be spontaneous, what we could do is go back to this, and this would still be negative. We'd pretty much plug everything else in, except we would set E to 0 and then solve for this ratio. And we would need to find out just how small this value would have to get before it was spontaneous. But again, because it was negative, it's not spontaneous. Another example using the Nernst equation. This one is essentially how a pH meter works. So a pH meter sends an electrode in an acidic solution, and it measures electrical conductance, the cell potential, and by knowing that conductivity, the voltage that it's able to carry, it can figure out the hydrogen ion concentration, thus the pH. Well, that's what we want to do here. So we're going to say we have a hydrogen electrode. We're bubbling hydrogen onto a platinum electrode that serves as a conductor, and it's coupled to zinc. So we want to know what is the concentration of this acid if zinc is getting oxidized and hydrogen is getting reduced. So again, if we're writing if we're starting with this, if we want to figure out Q is going to be the zinc concentration, which is 1 molar, times the hydrogen pressure, which is 1 atmosphere, divided by the H plus, and that's what we're looking for. And notice the squared. Now you might be wondering, why is it squared? And that's going back to equilibrium expressions. If there is a coefficient, in this case 2, we raise it to that exponent. Again, if we were to write out the half reaction, we would see there's 2 electrons being transferred, so that's why it's divided by 2. And when we measure this, we're finding that the voltage is 0.54. Again, the one over here, the 0.76, this is the one at standard conditions, where it's 1 molar, but we don't know what ours is. Ours is not 0.76, ours is 0.54. So again, we're gonna plug some stuff in. Oh, this is not super pretty. So again, ours is measured to be 0.54, but the standard condition, the standard cell is 0.76, which is again what was being shown here. And then we just have a whole lot of gross math. So we need to know, okay, well, first we can plug in the value for zinc and hydrogen. So that's one, zinc and hydrogen gas, 1 and 1. And so then we get this. So we can condense some things. We get these values, so we can multiply by both sides by 2, divide by 0.0257, and you're going to get some value is equal to the natural log of the inverse square of hydrogen. And so I'm just going to jump through, and again, we're pretty much going through some algebraic steps. So that gives us 17.1. You take the Euler's number to get rid of the natural log. Then we have to take the inverse square root to eventually find our hydrogen ion concentration. So 2 times 10 to the negative 4. So we could then take the negative log of that to get the pH if we wanted to. So honestly, I feel like this problem is pretty straightforward, but the math is kind of gross, and so I probably will not give you one that looks like this. I can't say there's not. I'd have to go back and look to see if there's one in the homework like this. But yeah, make sure you can use the Nernst equation. Now, a concentration cell is kind of neat because it comes up in a lot of biology and biochemistry topics. I have a video down at the bottom talking about the nervous system. It's a crash course video because our whole nervous system is a bunch of electrical impulses, but it's not because it has um, multiple components that are different getting oxidized and reduced. Instead, it sets up our body sets up a concentration cell across the membrane. So you have higher concentrations of one substance on one side than the other, and the gradient, that difference, leads to what we call cell potentials or membrane potentials. So you should watch this video if you find yourself having extra time. So in this case, let's look at, you could have two cells where in one side you have an anode with 0.1 molar zinc ion and a cathode that whereas 1 molar zinc. And so we have 0.1 molar and 1 molar. So there's a factor difference of 10. So overall, we're going to see that the zinc 2, the higher concentration is going to get reduced, and the lower concentration is going to get increased. So overall, the reaction is going to keep going until the cell concentrations are equal, and only then will E equal 0. So these, you're not going to generate huge cell voltages with a concentration cell, but again, what's neat is you don't have to have two separate materials. Again, for the ones shown, again, we would set this up. Now, if I were to ask you, hey, what would be, oh, this would be a good test question. What is the standard cell potential of a concentration cell? And there's no math required, because if it's a concentration cell and you're looking at the same component, then the difference in their standard reduction potentials is always 0, zilch, nada. So this is going to be 0. But here we're looking at 2 electrons being swapped. This is the concentration of it being dilute on top. And so that's 0.1. And the concentration where it's concentrated, and that's 1 on the bottom. And so we plug these magic numbers in, we get a 0.0296 volt potential. So this is, again, still fairly weak. I mean, if we're talking about a double A battery, they have voltages of about 1.25, and this is much smaller. But again, you should watch this video. But yeah, that's all I have for concentration cells. Let's talk batteries. So batteries are just controlled redox reactions where you um, strategically layer your anode and cathode to be separated where you need something to make contact before they can produce an electric current. Um, Again, most commonly we use what are called dry cells. This is an Leclanche cell where zinc is the anode, that is, you could say, providing the electron source. And then the cathode's a little more complicated. It has manganese oxide along with ammonium that can absorb the electron to produce a few things. But these are called dry cells because instead of the galvanic cell where you have solutions, instead you have this moist paste. You have electrolyte paper that's been soaked, so there's not actually any free-flowing liquid inside these things. So again, this is a just 1.5 volt battery, but there's a variety of types. Another type is the mercury battery. Now, mercury batteries, um, they're not a whole lot different besides the setup. They still use an electrolytic paste. Um, they're called mercury batteries because of a mercury oxide that's used throughout. And these have the benefit of having greater capacities and a more constant voltage, but they have to be encased in stainless steel, which is one of the, they're a little bit more, they're more expensive than other dry cells. And because of that, they're not more as routinely used. But if you're talking about medical equipment, things where you, or things like pacemakers, hearing aids. There's a lot of small electronics you would find these mercury batteries. These are the kind of button looking batteries. And again, here's some half reactions. You don't actually have to know the half reactions, but yeah, those look nice. Yep. The lead storage battery, or as most people would know them as the car battery. Now, these lead batteries are not dry. They actually, instead of a paste, they are. If you've ever picked one up, you could slosh it around and um, feel the sulfuric acid that's sloshing around. So it has sulfuric acid that acts as both an electrolyte, but it's also going to function to make it rechargeable. So it has a series of 6 cells, each one alternating. And so if each one is 2 volts, it can construct a 12-volt battery. Um, Again, these are lead batteries. Lead serves as the anode. It gets oxidized, but they're rechargeable. So if you apply a current, which typically your car really only runs off the battery to get started, but once it's started, your alternator converts rotational energy from your car moving to electrical energy, and again applies a higher voltage to pretty much send this reaction backwards. Now, when eventually the sulfate gets used up, and that's generally when these lead batteries start to go bad. Um, another drawback is they don't function well at really cold temperatures because the liquids become more viscous, and when that happens, then sulfuric acid is not nearly as conductive. And so some people have problems starting batteries. They're starting their car in the winter, and it's not because it's necessarily dead, it's just because cold temperatures affect conductance. There's the lithium battery. Now, these, again, are by far the most, in the last 10 years, have taken over as like almost universal. If we're talking cell phones and other laptops, electronics, or more expensive AA and AAA batteries, they have very high reduction potentials compared to lead and zinc. Again, so they can have higher voltages. They're low weight because lithium is a very light metal. And I misspelled rechargeable. And well, hold on, pause. And that's better, rechargeable, which is not something that rechargeability. Now, technically, all batteries could theoretically be recharged, but things like zinc um, batteries, they they develop they develop defects that can cause hazardous issues if you try to recharge them. But lithium is a much safer alternative. We generally only use lithium because they don't develop the same type of oxide layers when you try to recharge them. And you don't have to know the cathode and anode half reaction for any of these, but there they are. Oh, you should watch this. How do lithium batteries work? I thought if we were in class, we would watch that video, but we're not. Well, I mean, I guess you're in class, so yeah, watch it. Maybe later. There's the fuel cell. Now, I remember when I was a kid, the like this was something that people talked about as like the future of car energy. Like in the future, all vehicles are not going to run off gasoline; they're going to run off fuel cells. And some people even had was not very common, but a few people had these like tanks of hydrogen gas on their car, and it would run off this. Now, this process, it is technically what I wouldn't call it a It's not a battery because it's not stored, and it requires a constant supply. But it is very energetically efficient. Overall, the reaction is just burning hydrogen. Hydrogen and oxygen make water. So the exhaust, it's just giving off water vapor. So it literally gives off steam is its output. Typically catalyzed by uh, a metal. Uh, Last semester we'd call it a heterogeneous catalyst. Um, it's essentially you have again your anode is hydrogen gas, and your cathode is oxygen, and make that go away. And overall, you're getting the quote combustion of H2. So, but you're technically not burning it; you're allowing it to undergo that electrochemical process, pretty much on the surface of a metal. And again, that difference in voltage or the cell potential is enough to drive this. Now, um, I've seen several videos about what happened to fuel cells. Where'd they go? I thought this was going to be the next big thing. And what it came down to, at least a lot of them talk about, is infrastructure. That if we wanted, it would be a lot harder to implement hydrogen fueling stations all around the country. When it'd be way too expensive. It wouldn't be worthwhile over what we already got going for us. But anyway, fuel cells. Corrosion. So this is a couple things about, again, when we talk about iron rusting, that we call that corrosion. That's this deterioration process. It is electrochemical. It's redox. We get iron turning into things like iron 2 and iron 3, where things like oxygen, here serving as the cathode, they they get reduced. Now, iron specifically is very porous, and that's why it can continually corrode through. So as it rusts, more and more oxygen can still get through to continually kind of eat away. And so there's a number of different things you can do to prevent this. So for one, you can use stainless steel, which has a small amount of chromium, which when chromium forms an oxide layer, it is not porous, and it kind of prevents it from oxidizing anything further throughout. Galvanization is when you coat things with another metal, in this case zinc, usually zinc, and that way it kind of sacrifices itself, and you end up with a zinc oxide layer, but also it's not nearly as porous as iron, and it doesn't continue to corrode through. Passivation. It's you treat it with something that will automatically form an oxide layer, and it's kind of like pre-rusting it, but very uniform that it doesn't necessarily look. It's not going to look like rust. So those are preventative measures. Another one, I've always liked this. If you need to store something underwater, here's a iron storage tank. Well, if you just leave that out over a couple years, this thing is going to corrode and you'll end up with holes and then it's trash. And so what we can do is we can all you got to do is attach another metal that has a higher reduction potential. And this is a sacrificial anode. So if anything tries to corrode the iron in this tank, if something tries to steal its electron, if it's in contact with this piece of magnesium or some other metal, it can then pretty much instantly take an electron from magnesium to keep itself in the reduced state. So magnesium gets oxidized. And over time, it will be this that gets corroded away, but it's much, much, much easier to replace versus, this apparatus. Uh, okay, almost to the end. The last components of this chapter look at electrolysis, which is what if we have a non-spontaneous reaction that we want to make spontaneous? So, for example, what if you want to take table salt where sodium and chlorine are very happy being positive and negative? What if we want to reverse it to separate them? Now, if we go and look up what's the standard cell potential, it's negative 4 volts. Now, that negative tells us, nope, that's not happening. But what it also tells us, that's how many volts you have to apply to make this happen. So here's a setup where you have molten table salt. So heat table salt up to like 400 Celsius, get it nice and liquid. Um, and then run at least 4 volts through it, and you'll get this separation of chlorine gas coming up the middle and liquid sodium, because at high temperatures, or it's already liquid, but sodium has a lower density, and so it will naturally float up in this. Here's another look at the same thing, but in the more this is just looking like a galvanic cell. It's a little bit more straightforward. But again, so this redox reaction would not normally happen, but if we apply the voltage, again, the opposite of what we calculate, go back, then we can make this go forward. Again, with water, you would not expect this reaction to happen. Water forming oxygen and hydrogen. Again, the Gibbs free energy, the standard free energy is 474 kilojoules. So again, what that tells us is you need to put in that much energy to be able to get this to happen. Now, in terms of electrochemical, if you go and look up the value for water standard reduction potential, it's 1.23. And it's actually for the reverse of what's shown here. This is because it's going this direction. This would actually, I guess, be negative 1.23. Hydrogen, we called this She, the standard hydrogen electrode. It is what we said a 0. And so if we calculate our cell potential, 0 minus 1.23 is negative 1.23. So this is a non-spontaneous process. However, if you put at least 1.23 volts into the solution, then what you're going to get is it's the electrolysis. And the fun thing is on the different electrodes, you get bubbling on both electrodes, but you get a different gas on each one. So on the anode, we're getting oxygen gas, and on the cathode, we're getting a hydrogen gas. It's you could sort of see it here, but you can also do this and see the stoichiometry. You're going to get twice as many moles of hydrogen as you will oxygen because it's in a 1 to 2 mole ratio. So if you were to collect these, you would find those volumes are found in a 2 to 1. Now, for the electricity, because water is a very, very weak electrolyte, you'll typically always have um, it'll say, like, this says dilute sulfuric acid, and that's just to serve as an electrolyte. I think I saw on this little animation it says, so at some point it says sodium hydroxide. Okay, so let's get to some of the math. So I think, yeah, I just have two problems to go. So we want to look at how can we quantitatively assess electrolysis. So we're going to be dealing with current, which is measured in amps. So your standard like iPhone charger or iPad charger is like 2.1 amps, and that tells you how many electrons are flowing per second. So if we want to know how many electrons or what's the charge in coulombs, then charge in coulombs is current times time in seconds. If we then want to know how many electrons there are, then we're going to use Faraday's constant, um, because that's 1 mole's worth of electrons charge. And then once we know that, we're going to use the mole ratio and half reactions to go for the moles of the actual substance. And then we'll use either molar mass or the ideal gas law to figure out how much of something there actually is, grams or liters. So let's try that. So we run a current of 1.26 amps through an electrolytic cell with sulfuric acid, which again is just the electrolyte, for 7.5-ish hours. What volume of oxygen is generated? So we're going to use the current and time given. Oh, go away thing. We're going to use the current and time given to then figure out how many coulombs it took to figure out how many moles of electrons, figure out how many moles of oxygen, and then liters of oxygen. And I have the half reaction shown. And the important thing is for oxygen is it's taking 4 electrons in this process. So we have 7.44 hours. There's 3,600 seconds in an hour, so that's 26,700 seconds. Well, a 1.26 amperage times that time gives us a total charge of this many coulombs. So if we want to know how many electrons, well, dividing by Faraday's constant, again, to group that into the mole, we divide by 96,500 coulombs in an electron. Again, and then we can say, well, there's 0.35 moles of an electron, or that many moles of electron. Now we're trying to figure out what's our volume of oxygen. So keeping in mind that 1 mole of oxygen took 4 moles of electrons, then we have our conversion factor, 4 moles of an electron, 1 mole of oxygen, we get 0.0873 moles of oxygen. And at this point, we have the ideal gas law. So to get our volume, if it's normally PV equals nRT, we have nRT over P. So we have the number of moles, the gas constant, the temperature. Standard temperature is 270 is 0 Celsius, so that's 273 Kelvin, 1 atmosphere, and so that means we have just under 2 liters worth of gas. Okay, last problem, I promise. Electrolysis of silver nitrate. So let's say we take aqueous silver nitrate and we plug it up to our iPhone charger, and we eventually are able to reduce 0.67 grams of silver. So we want to know what quantity of electricity was used in coulombs. I mean, we could take that to just number of electrons, but we're not going to right now. And how long would it take with our charger? So again, we need to know that the half reaction is a silver ion plus an electron makes silver. And we're going to go from the grams of silver to moles of electrons using this relationship, and then we can get the number of coulombs. Now, to find the length of time, we just need to know that the charge is equal to the current times time. So current times time is charge. And so we'll use that relationship in just a second. Are you kidding me? I had this looking so pretty in PowerPoint, and then I had to drag it to Google Sheets, and it made it all look like trash. If you want to see this look prettier, go to the notes that are posted, because this looks awful. Oh, come on. Okay, I'm going to pause and fix this. Okay, that looks better. So 0.67 grams of silver. We're going to divide by its molar mass to get moles of silver. And then looking at the half reaction, every mole of silver is produced by 1 mole of electrons. And then using Faraday's constant, a mole of electrons has a charge of 96,500 coulombs. So we multiply and divide, and we get just under 600 coulombs. Now, again, if we wanted, we could have alternatively multiplied by Avogadro's number. We could have also seen how many electrons it took, but that would be a different question. Now, to see how long this would take with a standard charger, again, instead of coulombs is amps times seconds, the time is the current divided by amps. Our charge divided by current. And so we have 599 coulombs divided by 2.1 amps. We get 290 seconds, which is just under 5 minutes. Okay, and so with that, that is the rest of this chapter. You should watch this video about how to make a lemon battery, or I've also seen them done with potatoes and all the other fun stuff. But that's this whole chapter. So the homework is, well, uh, the homework I think I have set due to be Tuesday. I also plan to post the quiz later today, and you'll have till Tuesday to get that turned in. Okay, have a good day, everyone.